Okay, so now for the last lecture in our correlation structure unit on autocorrelation. So as usual, no required readings for class, but again, there's some really nice optional readings that can be really, really helpful if you're confused at all. I use them quite a bit in thinking about this work. Okay, so autocorrelation. Let's start by thinking about what it means to not be autocorrelated. So when data are not correlated, and there is no covariance between points, then there is no autocorrelation in our data. Data are said to be random, in quotes, and this is also called white noise, if you've ever heard that phrase. So this is the assumption that we tend to make in most of our models, that there is no autocorrelation. And so this is data of a process simulated through time or space or whatever you want to think about, and this is simulated with absolutely no autocorrelation. And so you can see that every point relative to its neighbor is random. There's no trend in that data at all. But a lot of times we have data that's positively autocorrelated. So if data are positively autocorrelated, that means that data that are close in time or space, etc., are more likely to be similar. And this is also called red noise. So here's some more data simulated from a positive autocorrelation or from a red noise process. And you can see that points that are next to each other tend to be more similar than points that are far away. And so you sort of see this almost cyclical pattern arise from this nature of this positive autocorrelation. And the opposite of positive autocorrelation is, of course, negative autocorrelation. So if data are negatively autocorrelated, that means that data that are close in time, space, etc., are more likely to be dissimilar. And this is also called blue noise. And so here you can see that points close in time or space right next to each other are actually quite different from each other, right? So these points tend to go up and down, up and down, up and down over the mean, which is 0.5 here in this simulation. And so, right, this tends to sort of produce this really zigzag process because points tend to be close in space or time tend to be different from each other. And so we don't see a lot of negative autocorrelation in the work that we do and a lot of the data we have. But I wanted to, positive autocorrelation is much more common, but I wanted to sort of demonstrate what this means so you can see what the opposite is, so you can better understand what positive autocorrelation is. So, as I mentioned, in our work, we will most likely have to account for positive autocorrelation, as it's pretty common for data to be correlated positively through time or space. So when analyzing data through time or space, we need to think about how to account for this autocorrelation. And so some examples of when we might need to think about positive autocorrelation, for example, average daily temperature. So if your y variable, your dependent variable is temperature through time, you can imagine that my temperature today is more likely to be similar to my temperature yesterday than it is to be similar to the temperature in 5 months from now. So that's just the idea of positive autocorrelation. Things tend to be more similar to each other. The likelihood of rainfall events. So if you're thinking about on the order of hours, say, the likelihood that it's going to rain in 2 hours is more similar to the likelihood that it'll rain in 1 hour or to what's happening right now versus in, say, 10 hours or 30 hours. So if we want to think about space, you can think about moisture content in the soil. Points close to each other are more likely to have similar moisture content because these points are coming from the same watershed, they have the same topography, etc., versus points that are far away from each other. And in a very relevant case to now, if you think about disease spread across the country, so points that are similar and are more closely linked in space are more likely to have higher disease prevalence, disease counts, and increased disease spread because they're closer. And so these things can move more easily in points that are close versus points that are far away. So a common way to deal with autocorrelation is through autoregressive and moving average models. And so this is termed ARMA. So the AR part of this is the autoregression, and that's a model that uses the dependent relationship between an observation and some number of lagged observations. So in simpler terms, this makes predictions using previous values of the dependent variable. So if you think about our temperature example across days, our dependent variable y of temperature is going to be, for t plus 1, is going to be made given some number of lagged observations. So t0, t minus 1, t minus 2, etc. And so the moving average part of ARMA is a model that uses the dependency between an observation and a residual error from a moving average model applied to lagged observations. So in simpler terms, that means that it makes predictions using a series mean and previous errors. And so you can think about moving averages as like a sliding window across that series of your data through time or space. So it takes small windows and estimates what the mean of that smaller series and the error is, and then moves the window to get another series mean and error and so on. So it sort of uses a sliding window to take advantage of the moving average to sort of track that positive autocorrelation through time. And so basic autocorrelation models, which is what we're going to be talking about, that we will think about, will be either in the autoregressive format or autoregressive moving average. So we're going to either do AR or ARMA. And so one thing to keep in mind is that these ARMA models assume stationarity of your time series or space series. And there are 3 requirements of the stationarity. So that means that the mean of the series should be constant, not a function of time or space. The variance of the ith series, that should be ith series, should be homoscedastic, so not a function of space or time. Right, because your series is, in like a moving average model, your series is moving, your small chunk is moving across your series of data, and so the variance should not be a function of time or space. It should be even across your series. And the covariance of the ith term and the I plus mth term should not be a function of time. So again, no covariance through time. And so this can be tricky. Like, think about temperature based on year. We know that temperature is increasing through time because of global warming and climate change. And so if your data isn't stationary, then you need to detrend. So we will assume that you can do this using logging your data. There's lots of ways to detrend. You can do differences, but we're not going to worry about this too much. For this class, we're going to assume that our data is stationary. However, I will just point out that sometimes your data will not be stationary depending on what you're thinking about, for example, climate change. So a note about autocorrelation in time and space. I just want to point out there are many, many great ways to investigate time and space series data, such as using the current time series to forecast future predictions in the data. So here are some useful R functions to help you forecast with time series. There's a lot of information out there on how to do this. There are whole courses on dealing with time series data. So in this course, we're just going to be covering the very basics of accounting for autocorrelation in time or space, because we're talking about linear models, and this is most likely what you're going to need to do, how to take into account this correlation within mixed effects models or linear models. There's a note at the end about that. But I just want to point out that, if you have really interesting data across a series of time or space, I recommend thinking a bit more deeply about how to analyze it other than just what we're talking about, and perhaps come chat with me and we can sort of think about what might be some more interesting and really creative ways to do that. Okay, so let's go back to our positive autocorrelation example. Let's consider the case where the data that are closer in time are more likely to be similar to those farther in time, right? Positive autocorrelation. And again, I want to just point out that this is identical for space. There's no reason you can't substitute space for time here, but we will be using time in our example because that's the data we have. So we're going to go back to our snail example. So if you recall, in our previous mystery snail examples, we had more of a simple correlation structure where our residuals were different among groups, but they were similar within each group. So if you remember, there are 6 measurements of biomass consumed through time per individual. So here I have, in this figure, I have marked out each individual, and you can see that each row and column indicates time 1 through 6. And so you can, so it's potentially more likely that measurements closer in time are more likely to be more similar to each other than those that are farther away in time. Perhaps snails get really good at consuming biomass through time because they're aging. They figure out how to eat more efficiently. So time, or as you can see here in this figure, times that are closer, like time 5 and 6, are more likely to have a higher correlation than times 6 and 1, for example. So we're going to figure out how to account for this structure of autocorrelation in our example that we used in the past. So we're going to be talking about these kind of correlations with mixed models in LME. So yep, we're back to LME. And so I've included the link for the page for the documentation on how to specify the correlation argument, and another link for different types of classes of correlations. And so basically what we have is we're going to specify our LME again here. But we're going to, instead of adding that weights function that we had before, we're going to add our correlation function, correlation argument. And so when you're looking at the different types of correlations that you can use, you're most likely going to want to use those core AR1, right? So an autoregressive correlation, or core ARMA, so an autoregressive and moving average. And so we'll use the former here, but try the latter on your own. You have the code, so you can try it on your own. But so here we're going to specify our LME with biomass as a function of sex and month. Our data are the snails again. We still have a random effect for our individual with a random intercept, and now we're adding correlation, which is this core AR1 in the form of month, which is the time value, right? Month 1 through 6 is what we have. So we're using an autoregressive model to deal with that correlation. So it's going to think that times 1 and 2 are more likely to be similar than times 1 and 5, times 3 and 4 are going to be more similar than times 3 and 6, etc. So this is our model output when we run it. So you can see that we're still seeing the same model results, but it is taking, right? So we still have that male snails consume less biomass, and that consumption of biomass increases with month. However, we're just taking into account our correlation structure in a way that's more accurate. And so that's how you're going to deal with correlation in time or space in these linear models. One other type of correlation that's really important to think about is phylogeny. And so taking into account the phylogeny of your data is another form of correlation. Unfortunately, it's a bit more complicated because now we need to think more deeply about matrices and how to work with them. Instead of just having a series of data 1 through 10, in your time series 1 through 100, in your space series, etc. Now we need to start thinking about a matrix of species or individuals or whatever, and how closely they are related. And so we need to think more deeply about matrices. So what we're going to do is come back to this in our multivariate unit, because I want to make sure that we cover the basics of how to deal with matrices first, and then we'll think about phylogenies. But I wanted to include this image here from a paper from Ives and Helmus in 2011. And so what they're showing is that you can have say you're looking at species in lakes across, or algal species in lakes across a bunch of different lakes, different sites. And you can have your species of algae, and they can follow this phylogeny at the bottom. And then you can have different sites that have different abundances of those species. And you want to find out if there's you want to take into account the correlation that comes with this phylogeny. So you can see that some sites in the bottom half of the sites tend to be higher in certain sets of the species versus the other. And so we want to be able to detrend and get an account for that phylogeny, so we're not biasing our results based on many more species that are similarly related. because there's covariance between those species, right? They're not completely independent. They have similar life history strategies, similar evolution, it's just similar strategies. So that's all we're going to talk about today, but I want to add a short note that if you have a correlation structure or weights similar to what we've been talking about this week with both structured residuals or autocorrelation, and you want to use just a linear model without random effects, you can use GLS. It's basically exactly what we've been doing. It's just slightly different formatting, right? Because you don't have your random effects. So I've included the documentation and you can definitely check it out. Because I feel like linear models with mixed effects with random effects tend to be more common, I stuck with the mixed effects here, but you can just use a simple linear model. And with that, please complete quiz 7.2 on Canvas. And this is the last lecture for this week.